study statics. Let's start with the definition of mechanics for today. And at this point, when I'm in the classroom, I start asking the students, what is the definition for mechanics? What is the definition for mechanics? What is the definition for mechanics? So I'm not there with you. So I'm going to start for telling you one definition for mechanics. And this definition is in the preface of one of the, not the book that we're using, but one of very famous books. And it says it's a branch of physical science concerned with the study of the state of movement of gases, liquids, and solids. And then I asked the students, what is the definition about this? What do they think about this definition? And they try to come up with something. But let me tell you something. If I read this definition when I was taking the statics course for the first time, I will close that book and I will think I will change major because that definition doesn't tell me anything. So let's try to form a definition. What is mechanics? Basically, mechanics, what we're going to do is we're going to study of what happened to a thing when forces are applied to it. That's it, period. Now, that thing is called body. Could be the forces could be big, small, the body could be big or small, but that's basically what it is. We're going to study the influence, the effect of forces acting on bodies. That's it, that's simple. That's better than the study of the state of movement of gases, liquids, and solids. So what are the branches of mechanics? Well, mechanics has basically three distinct branches. The first one is the mechanics of the rigid bodies and the formable bodies and mechanics of fluids. And within mechanics of fluids, we have two different types of fluids. What are those different types of fluids? Come on. You can tell Sarush. Sarush is your TA, by the way. You can tell him. Different type of fluids. What? No. Not alcoholics. This is not a. Yeah, it is a fluid, but this is not what we're talking about here. Another one. Fluids. Compressible and incompressible. What are compressible fluids? Gases. Theoretically, what are incompressible fluids? Liquids. Now, this is a study by mechanics of fluids. Rigid bodies, then we have to, by the way, what is rigid? Mr. GTA, please, can you ask them what is rigid? I can be here forever, you know. You are the one stuck in the classroom, so you better start having any opinion about what rigid is. No, rigid is not solid. It's not. I mean, that's not the definition of being rigid, because just imagine now that you have in the middle of the classroom a giant marshmallow and then you're pushing it. Is that solid? Yes, it's not gas, it's not liquid, it's solid. Is that rigid? Definitely not. So what rigid means is that it's not deformable. That's what rigid means. This part of rigid bodies is dynamics and statics. What I mean is not deformable. Deformable means it doesn't change the shape. That's what it means. The shape is constant. And this part of the formable bodies is what you're going to be studying in mechanics of materials or strength of materials, depending on what class are you taking, what is the major. They name it differently. It's also called mechanics of the formable bodies or solid mechanics. And then you have statics and dynamics. What is the difference between statics and dynamics? No. Come on, guys. Why? Because it's moving is not static? No, that's not the definition. That's not the difference. The difference here between dynamics and statics is this phrase, or these two words, unbalanced forces. In statics, everything is in equilibrium. Means there's not acceleration. That's the definition. You can have the body at rest, or the body can be moving at a constant speed, and we still be dealing with a statics problem. Okay, we are going to be dealing with 4 fundamental physical quantities, and those are length, mass, time, and force. And we're going to be working with 2 different systems of units. One of the systems is the international system, and the other system is the US customary system, which is the system that you are used to, or I think you are used to. In the international system of units, the unit of length is a meter, time is second, mass is kilogram, and force is Newton. In the US customary, which is called FPS, feet pound second. FPS system, length in foot, time in second, mass in slugs. Do you know that your unit of mass is a slug? This is a derived unit, remember that. So basically what you're doing is you are taking the force, which is pound, and you are dividing that force by the gravity. One thing is here that always seems curious to me is that you see every single unit is the root unit, but in the system, international system of units, the unit of mass is the kilogram, not the gram. Kilogram, 1,000 grams. I guess that is because of a gram is very small and they made it kilogram, but I really don't know the answer for that. Common conversion factors, I don't know. There are a lot of conversion factors. You can say that 1 foot is 0.3048 meters, 1 pound is 4.4482 newtons, or 1 slug is whatever is in kilograms. I basically know I think 2. I know that 1 kilogram is 2.2 pounds. I know 1 inch is 2.54 centimeters. And then I know, of course, that 12 inches are in 1 foot and 3 foot is a yard, etc. But the system, the international system is a lot easier than the US system, because, not because it's the one that I learned, but because it makes sense. It's based on the metric system, the decimal metric system. Let me put this in words if I can. You have 12 inches per foot, but then you have 3 foot per yard, but then you have 5,200 and something, 80 I think, foot per mile. What is the rationality there? Now if you go to the other system, then you have centimeter, decimeter, meter, units of 10, decameter, octameter, everything is in units of 10, kilometer, etc., etc., etc. I don't know, it makes more sense to me. Now, what I want you to do is this. You have to work the problems in the unit given, unless otherwise it's instructed. And we also have to be very careful with the approximations and rounding. For example, convert a torque of 47 inch-pound into SI unit. What is the first thing that you have to do? You know, I'm making this dramatic pause here so you can talk. What is the first thing that we have to do? No, it's not converting the inches in feet. It's not converting the pounds in kilograms. It's knowing what are the units in the SI system that we have to convert. So if we are inch pounds, the first thing that we have to know is that in the SI units, if we're talking about torque, it should be Newton meter or meter Newton. Now we can start. Now we have 47 inches per pound. Do I have anything here that converts inches in Newton? No, but I have one thing that converts pounds in Newton. So the first thing that I can do is convert these inches in foot. What should I do here? I know 1 foot is 12 inches. What should I do here? Multiply or divide? No, it's not divide. Once again, it's multiply because this is already in the denominator there. So I multiply these, and these inches and these inches cancel out, and now I have feet and pound. Okay? Now, what is the next thing? I convert the feet in meter. Why? Because I know 1 feet is 0.3048. Remember, this is feet in denominator, this is denominator, so I have to multiply again here, and those feet cancel out. Now I have pounds and I have meters. Well, now I convert the pounds in Newton, which pounds in denominator, this in numerator. I have to multiply again and do that. And this is the answer. Is that answer correct? Maybe. I'm not talking about the calculations, I'm talking the answer. Why I say maybe? Because look at the amount of decimal places. How come I came with this precision and this accuracy here if my decimals are, and my numbers, original numbers are like that? Well, that's another discussion. In my case, I don't care. But be careful when you solve mastering engineering problems, because mastering engineering problems is gonna start talking about, it's gonna force you to express the results in the appropriate number of significant figures. And what is the appropriate number of significant figures? You have to review that because you learned that in physics. Anyway, no matter what, I posted a handout, small handout for significant figures, and it's already posted in Canvas in the tab that says lecture notes. You can go there and you already have it there. So one of the things that you have to do is that you don't use plurals, so you don't say kilograms. KGS, no, you say kg. Of course you pronounce kilograms, you say 5 kilograms, but when you copy, you don't put the S here. You have to separate the units with a dot, because this is meters second, for example. If I don't put the dot, what would be that? Yeah, that would be millisecond. Most symbols are in lowercase, exceptions with the numbers and some of the prefixes, but the names, because it's in Newton, Pascal, right? And some of the prefixes, mega, gig, etc., etc., etc. Exponential powers applied to units. Remember that and review that, because one of the big errors that people usually do during the test is that they don't know how to convert the units. Remember, if you say that 1 meter is 100 centimeters, 1 meter square is going to be 100 centimeters. Everything is square. That means it's going to be 10,000 square centimeters. Think of that, think about that, and review that part. Compound prefixes should not be used, like microkilogram. But if this existed, what would this be? Micro, kilogram. Micro, 10 to the negative 6. Kilo, 10 to the third. So that would be 10 to the negative 6. 10 to the third, that would be 10 to the negative 3. That would be milligram. Other rules, check your textbook, please. Dimensional homogeneity, yes, we have to have. That means everything has to be expressed with the same units. Appropriate number of significant figures. Once again, I don't care about these. What I suggest you to do, in my case at least, is use all the decimals that you can use, and then round the result in any way that the problem is asking you to do it. Be consistent when you round up. Everybody knows that if it's greater than 5, you round up. If it's 3528 and you have to round here to the 10th, then this is bigger than 5, and then you have to round this to 30. Or if it's smaller than 5, you have to round down. Let's say that you have to round up to this point, then you just leave it like that. So what if it's equal to 5? Well, you have been living a lie if you think that you have to round it up. It's not like that. Now, if you want the answer for that, go to your textbook. And in your textbook, it's explained exactly that. And I don't want to tell you the answer. I want you to go and investigate it, because in that way I'm forcing you to go and investigate the answer. This is the Polias approach for solving problems: interpret, plan, execute, and test. And that's basically what we have there. Now, that's the first chapter. First chapter is done. Now we're going to start second chapter, chapter 2. This is summer, so we have to cover a little bit more of material. In this part, we're gonna talk about the definition, and we're gonna discern between what is a vector and a scalar. We are gonna resolve the 2D vectoring components and add to the vector using Cartesian vector notations also. What is a vector? No, vector is not an arrow. That's always people say. Vector, an arrow, vector. No, that's not a vector. Vector is a quantity that has magnitude and direction, and also another definition is an oriented line for vector. So what is a scalar? Whatever is not a vector, yes. That's a scalar. Whatever is not a vector is a scalar, yes. It's just a quantity. That's it, positive or negative number, a quantity, a real number. Examples of scalars: mass, volume. Example of vectors: weight, for example, force, velocity. Characteristics of scalars: it's just a quantity. Characteristics of vector: has magnitude and direction. Addition rule: how do you add scalars? With the calculator. Yes, good, very good, you're smart. How do you add scalars? Come on. Arithmetic, that's it. How do you add vectors? With difficulty? I know. How do you add vectors? You add vectors by using parallelogram law, for example. Special notation for scalars? Very good. No, that was the first answer that you gave me correct today. What is the special notation for vectors? Well, in this book that you're using, the Hibbler, they use bold letters like these, yellow letters, or bold letters for vectors. You can have that, or you can have an arrow on the top of the letter also to identify vector. Okay, which of the following is a scalar quantity? Mr. GTA, please. I want you to ask them to raise hands for the options. Which of the following is a scalar quantity? I want you to please check what I'm telling you when I say option A, and they want you to tell them to raise their hands or to verify, because I'm going to tell them to raise their hands. So you verify they are raising their hands and start noticing this is participation. Participation is really important at the end. Why at the end? Because at the end, guess what? These participations could be the difference between a 67 being a C or 67 remaining a D. It's up to you. So I'm going to say option A. Everyone that believes in option A thinks that option A is going to raise your hands. Who say option A, scalar quantity? 1, 2, 3. Okay. Who says B? Okay, option C. Oh, a lot of people. Who say D? Okay. Okay. Let's start with the obvious. Let's start A. Force. If it's a force, it's not a scalar. We just said it. Where? Here. Force. Come on, I just said it. How are you going to say now that force is a scalar quantity? Now, let's go with weight. You say weight, but we also say that weight is a force. So, if force is not a scalar, weight is a force, hence force is not a scalar. Weight is not a scalar. Velocity. Velocity is not a scalar. Speed is a scalar. So, let's try again. Which of the following is a scalar quantity? A, B, B. Okay, now lower your hands. Let me tell you something. Whoever say B is also incorrect. What? Yes, it's also incorrect because position is not a scalar. And as we're gonna be checking later today, or tomorrow, maybe next class, not tomorrow, next class, you're gonna realize that position is not a scalar, because position also refers to a spatial location, and it's gonna give you the location of a point with respect to another point, which basically is telling you that there is a direction associated with that. Let's be honest, if I have to select between the four of us and they tell me there is a right answer and I have to mark one, I will mark B also. But remember, B is not scalar. For a vector addition, you use the Newton's second law. Yes. No. For vector addition, we just say that we use the parallelogram law. Okay. Vector operations. You are experts in vectors. So you say. You learn how to add vectors, right? I say right. You say yes. You learn how to add vectors, right? Multiply, subtract, divide. No, you didn't learn how to divide vectors because you don't divide vectors. So basically, vector operation, you learn how to multiply and divide a vector by a scalar, but not by another vector. You can multiply but not divide. You learn vector addition, you learn vector subtraction, you learn resolution of a vector, which is decompose a vector in components. So vector is really easy. If you had that vector A, for example, and I want to multiply that vector by a scalar and find 2A, what is happening there? Basically what I'm going to get is a vector that is twice the size and the same magnitude as the original vector. Easy. Now, if I want a vector negative A, and this is the original vector A, basically what I'm going to have is something like that. Can you let me finish, please? I was drinking coffee. Something like that. Because the magnitude is the same one, but the direction is going to be the opposite direction. If I have negative 1.5, well, it's going to be like this one, but the magnitude is going to be 1.5 times. Easy. This is just a quick review because I know you are experts in vectors. Another thing about vectors, rectangular components, you know that the vector can be expressed as the component x goes in the I direction, y, j, and zk. Yeah, you can do that. xi, xy, and zk. If I have to represent this vector here, that vector is going to be 4 in I, but I goes in x, so it's going to be here, 2 in j, but goes in y, and 5 in k. If I want to know the direction of the vector, I just move these towards this position here, and I get this 5, put it here in this position, and my vector is going to be from the origin to here. Tail to tip. That's the direction. If I want to multiply the same vector by a scalar, now I have negative 1.5a. What I do is I multiply every one of the components by negative 1.5, and this is what I get. Once I have this, I do the same thing. I represent. The only difference is if this is negative 6i, and this is positive. Remember, one of the things about the axes, first of all, they are referential axes. And secondly, whatever you have the letter, it's going to be the positive direction of the axis. So if this is the positive direction of I or X, the negative direction is going to come in this direction. Same thing happened with the J. If this is positive, the negative is going to come in this direction. And same thing happened with K. And this is going to be my vector. Look at this. Opposite direction completely to the original vector because it's negative here. Application of vector addition. Well, you have an example there of the application of vector addition. You see, when you see this, and I'm in class with you, I spend some time debating about which of these forces or these elements is the most important force for ensuring the equilibrium or the stability of that structure. And then I start asking, what do you think that is going to be F1, F2, F3, or F4? And people say, oh, F4, because F4 is the one that is in the top one, and if F4 breaks, the other one is going to force also the other cables. No. I'm going to make it easier because I'm not there with you. The answer is all of them are equally important. All of the cables have to be taken into account. And not only all of the cables. The cables and this part here, this bracket that is holding all the cables is also equally important. Now imagine that all the cables are made out of indestructible material. And this part also is indestructible, and they can withstand any force that you can apply. Okay, that's perfect. The cables are not going to break. This metal is not going to break. But what if this connection here just is loose? The structure is going to collapse. What if these bolts here that working shear you know, shear, right? Basically, you have the bolt in this part, and it's trying to cut this piece. Is gonna try to cut that part in that section in two parts. What if those bolts just fail in shear? What if these connections here fail? What if the concrete here, you know, is have the sufficient strength, but the adherence between this metal and the concrete or whatever the base is made out of is not sufficient? So, of course, here we are in statics and we have to add these forces to find this force. But I want you to start opening your mind to what engineering is. And this example is for civil, but civil, aerospace, construction, mechanical, all the engineers basically. So how do you add vector addition? Because you use the parallelogram law or you use a triangle. Parallelogram law says that if you have a vector A and B and you want to add them up, you just go and put vector A and put this vector B parallel to the vector A like that, and the resultant is going to be this one. Or I can start with B and add A, but notice that I go tip of the vector with tail of the other vector, tip of this vector with tail of the other vector. Or I can just put tail to tail, complete the parallelogram, and then I go from these tails, and my tip is going to be here at the other end of the parallelogram. How do you subtract the vector? Basically, you I'm sorry. Basically, you add a negative vector. Now, resolution of a vector. Resolution of a vector is kind of using the parallelogram law in reverse. That's what it says there. But it's basically breaking up the vector in components. Now, if I tell you, what is the x component? This is the force F, and this angle is alpha here, let's say. Pay attention. This angle here is alpha. So if this is F, how much is Fx if this angle is alpha? Yeah, not all at the same time, guys, because I can't hear you. If this angle is alpha here, this component x is going to be what? F cosine of the angle. And this component, which is this one, is going to be F sine of the angle. That is correct. That's what we do. Now, if the axes are not perpendicular like this one, and I tell you what is, if this angle is alpha here, if I tell you what is, and you know R, and I tell you how much is, I ask you how much is B, and you say B is equal to R cosine of the angle, you are wrong. And I'm recording this, and I'm going to show you this after the first exam again. Because if I ask you something like that in the first exam, and you do B is equal to R cosine of the angle, you are wrong. By the way, mastering engineering is correct. Don't start emailing me when you see a problem like this that is incorrect. What you have to go and is copy and now go and investigate how do you do that. Where are you going to investigate that? Your book has it. You saw it in physics. You're studying. Does law of sines ring a bell? No? Okay, it better rings a bell. And if it doesn't ring a bell, go and review it because you need to review it. Okay, so if you have to add several vectors, you can use parallelogram law and put the first one, put the second one, put the third one, and measure it, and the tail to tip again. But that's geometrically, that's graphically. If you wanna do it analytically, what you do basically is that you decompose each one of the vectors in the components. You break it out in components, so you get this force 1 and get the x and the y component. This force 2, x and y, this force 3, x and y also, and then you add everything that is x together, everything that is y together, and everything that is z together if you're working in the space. So basically, the x component will be f1x plus f2x, or minus in this case, plus f3x, and the y component is going to be f1 plus f2y minus f3y. So you have those components, and that's going to be the resultant force. If you want the magnitude of the resultant force, basically you take the, I personally like to write it here, my force. I don't know why it's not showing here, but it should be somewhere here. Oh, if it's not there, now it's there. There you go. If this is the resultant force from here to here, and that's the resultant force from here to here, and I want to calculate the angle, which is the direction, I just take the inverse tangent of FRY divided by FRX, period. Let's do an example. Determine the magnitude of the resultant force and its direction measured counterclockwise from the positive x-axis. And then you have that example. First thing first, what are we going to do? How are you going to approach this problem? Well, basically, these type of problems, we approach it in the same way. Every single problem, basically. So what we're going to do is, first of all, we're going to decompose each one of the forces in x and y components. We're going to, for each one of them, we're going to calculate the resultant force in x, the resultant force in y, the resultant force in magnitude, and find the angle of direction. Let's do that. Let's start with the first component here. How much is this one? This component is going to be, you know this little triangle here? That little triangle, by the way, let me tell you something, because I don't want you to get false ideas. This angle here, 45 degrees, has nothing to do with this angle here. This angle 45 degrees is the angle that this bracket is making with the horizontal. In this particular case, it happens to be the same one as the force, but it doesn't have to be the same one. So don't start assuming that because this is the 45 degree, this is 45 degree. Don't assume that, because that's a wrong assumption. Calculate it all the time if you want to calculate it. If you want to calculate this angle, you can, because you have this and this. So you can say this is the inverse tangent of this one divided by this one, which is 45 degrees. But do not assume that this is 45 degrees. Then why the problem is giving me that? Because you have that information. I can give you even the dimension, the diameter of these bolts, the washers, the nuts, the thickness of this, the material that is bolt, because you have all that information. Part of your work as engineers is knowing what type of information you're going to use for solving the problem that you are solving. You don't use everything all the time. So basically, if I want to find this, it's going to be, if I want to use this triangle, I can make a ratio, and I can say it's 1 divided by the square root of 2 multiplied by 60. And it going to the left, that's why you have this negative sign here. Or you can say, okay, this angle is 45, it's going to be negative 60 multiplied by cosine 45. Now this one here, what is going to be this one here? No, it's not the same. Why is not the same? Well, it's this 1 divided by square root of 2 multiplied by 60. Yeah, but it's positive. It's positive because it's pointing in the positive direction of the y-axis. Good. Now, what about F2? Well, F2 have this component, which is also negative. And here you can do two things. You can say, oh, this angle is 30 degrees. So it's going to be 70 multiplied by cosine of 30, negative of course, because it's pointing to the left. Or you can use sine of 60, because if I use cosine of 30, I'm using this angle, but if I put this vector here, then I can use 60, and this is going to be the opposite to 60. So I can say 70 sine 60 if I want to, negative. And the vertical one here, positive or negative? Yes, negative, because it's going in the negative direction. Now, if I use 60, it's going to be sine or cosine? Cosine 60, because it will be this side, right? Or sine 30, if I use this one. Negative 70 cosine 60. What about the x component of F3? There's no x component. What about the y component of F3? Negative 50. Now, what do? We add everything that is in X together, meaning these, and these, and we add everything that it goes in Y together, this, and this, with the corresponding signs, of course, and we calculate those two values, and we calculate the resultant force. This material is posted, remember that. Now, what I do personally, and trust me, I have been engineer for some years now, I always copy my components because that's going to help me out with the direction at the end. So this is negative, go to the left. This is negative, goes down. If I want the magnitude of this, what is the magnitude? The magnitude is going to be the hypotenuse of that triangle. So it's going to be a square root of this square plus this square. And then I get the magnitude. And if I want the direction, well, that angle is going to be the inverse tangent of this divided by this, which is that, and the angle is going to be 22.4. Come on, guys, wake up. You're making me sleepy. Any question? Not to me, but you can ask the TA. Okay, that is wrong. That problem is wrong. Because if you read the original problem, or even if it doesn't say the problem is not asking me for this angle. It's a counterclockwise measure from the positive x-axis. And even if it doesn't say it, when you calculate an angle, the result should be always, unless otherwise stated, should be measured counterclockwise from the positive x direction, which is this one. So this value is correct, but the result is going to be plus 180, and that's the correct direction. You know something? I asked a similar problem, similar to this in a test, and like 60-something% of the class had it wrong. Easy like that? No, easier like that. Because I said, what is the direction? And then what do you think are gonna be the answers? It was a multiple choice question. The answers are gonna be 22.4, which is the one that you got. It's going to be 202.4, but it's going to be also 360 minus this, so it's going to be 337.6, and it's going to be also 90 plus this, which is going to be 112.4. So all of the angles might be possible, but only one is the correct, which is counterclockwise from the positive x direction. I'm warning you all of these things, and sadly, trust me, I'm going to come after the first exam if I ask you something like that, and I say, you remember what I told you? Okay. XX% of the class did it wrong because of that. So prove me wrong, please. Do it correctly. Okay, another problem. It says 3 forces act on the ring. Determine the range of values for the magnitude P so that the magnitude of the resultant force does not exceed 2,500 newtons per square. What? That's crazy. How are you going to solve this problem? In the same way, I told you, every single problem we solve it in the same way. So what we're going to do basically is decompose each one of the forces in x and y components, find the resultant force in x and y, find the resultant force, and find the force P such that this resultant force is smaller or equal than 2,500. That's it. I told you, basically every single problem in this chapter can be done, can be solved by using the same procedure. And remember, I say almost every single problem. So don't tell me, you say that every problem you can. No, almost. Okay, let's go there. Let's decompose each one of them. So let's start with this angle here. Why this angle? Because I personally like to name my directions, like to calculate my directions, positive or negative. I don't want to use 105 because math for me is too abstract. I like physics. I like to see things. So this angle here is going to be 75. If I want to calculate the vertical, the horizontal component of this force, Okay, let's do that. Let's work only in X because we are working faster now. I'm not gonna go one by one. I'm gonna get all of them together. So what do I have in X? And if I have to add all the forces in X in order to calculate the resultant force, I'm gonna have P. I don't know how much is that, but it's gonna go in X to the right. I'm gonna have 600, but the X component of 600 is gonna be this one. So if this is 45 degrees, the X component here is going to be 600 times cosine 45 because it's adjacent. And also I have 1500, but it's going to be this component that I'm looking for. So it's going to be 1500 times cosine also. I'm looking for the adjacent angle to the 75. 1500 cosine 75, but it's going to be negative because it's pointing to the left. There you go. That's the resultant force in X. 600 cosine 45 plus P minus 1500. What about Y? Well, in Y, the only thing that we have in Y is this component for 600. That component here is 600 sine 45 because I'm looking for the opposite to this angle here. And 1500, once again, sine 75, and that's going to be FRY. Once I have FRX and FRY, I calculate my resultant force. How do I calculate my resultant force? By squaring this and squaring this. Remember, resultant force has to be less than 2500. That's what the problem says here. The resultant force does not exceed 2500, meaning 2500 is bigger than the resultant force. That's what I'm saying here. But instead of getting the square root, I'm squaring resultant force, so I get rid of the square root that goes in this direction, and I present my equation like that. I square this, add them up, solve it, and find the force P. Any question? You can ask the TA right now if you want to. I'm going to give you like 30 minutes to think about that. You say 30 minutes? Well, we have to cover. I only have been here for what? 1 hour? This class is 2 hours and something, or almost 2 hours. That is wrong, or is incomplete. Why is incomplete? Because the problem says, first of all, it says that P is always directed to the right. And if I get a negative value of P, that basically will be directed to the left. So just, and if you want to be thorough, P should be smaller. The zero should be smaller, because if you say equal, then P is null. It's not directed to the right. So it should be smaller here. Those are technicism, but they are very important technicism. Okay. Some suggestions. With this, we're going to be finishing today's lecture. Some suggestions for you. First, attend the lectures. Why? Because I feel lonely and I want 200 students in the classroom laughing at my bad jokes. No. Because it's easier for you to be here. It takes longer to understand from the book. And on top of that, remember, we have pop quizzes. You're not in class or class activities. You're going to miss them. Develop a good feel for the subject. It's practical, interesting, makes a lot of sense. And besides, you have to pass the course anyway, so be here. Studying groups. That helps a lot. Studying groups. This class have a lot of opportunities. Hopefully next class I'm gonna invite people from the SI group, supplemental instruction group, and they do a terrific job tutoring students. So they are gonna come and they're gonna probably post the schedule for summer that they have. But you have the SI tutors, you have the SARC tutors, you have the Civil Engineering Chi Epsilon Honor Society tutoring also, you have the TA office hours, you have my office hours, you have plenty of help, but you have to use it. So use it. Studying groups. Some suggestions. It says do not procrastinate. Yes, do not procrastinate, especially with the hard copy homework. This class is extremely easy. And I'm saying it again. But I have had students repeating it 3 times. And trust me, I give you every single possible chance of passing this class. You can ask the TA because he's with me when I'm putting the final grades, and right? I go case by case at the end, and I try my best for you to pass the class. But 50 is not a passing grade, no matter what I can do. Okay? So give me something. Give me something. Show interest. Participate in class. Do your work. That's all you have to do. Do your work. Okay, guys. This is going to be all for today. Hopefully, I'll see you next class. Remember, you have Mastering Engineering class already posted. And no class, homework already posted over there. And I'm planning on assigning a homework of chapter 2 really